When I played this game of drawing the 2 cards, this was my results, which means how many times did I win? 3. So my probability of winning based on my 10 trials was 3 out of 10 or 30%. Can you guys do yours real quick? When we take the survey of the entire class and see how many wins we got when we ran this experiment in general, including me, that means it's a total of 99 wins out of how many games played? Well, 10 times the number of numbers we have here, and we have 28 numbers here, so 280 games. So in your calculators, can you do 99 over 280? Is it 0.35?
Yeah.
Exactly?
Yeah.
Nice. Okay, we'll leave it as 0.35. We'll say it told us to round to 2 decimals. So we had a 35% chance as a class of winning this game. This is the empirical probability because we got it from experiments. We got it from trials. But it's not necessarily the theoretical or the classical probability number that we would get. I said that sentence in a weird way, but we get it. For this game, because of the fact that we had no replacement, because these were not independent events, we can't just simply multiply the probabilities together without first realizing that there's a branching scenario to the wins. What I mean by that is we have to create this tree diagram to see the different combinations that we would have. We could maybe make the first card an ace, the second card an ace, or the first card an ace, the second card a king. King, ace, king, king. Do we see that? So what we want to do is fill out the probabilities for each individual event to happen so that we can then find the final probability or the classical probability of this happening. So just in general, what was the probability from the jump of this game of us pulling the first card as an ace? 2 out of 5. So we're going to put 2 out of 5 right here. What was the probability that we'd pull a king? 3 out of 5. That makes sense. They add up to 5. 100% chance of me pulling a king or an ace. Those were the only options. For my second card, let's say we do the first card as an ace and then the second card is an ace. What is the probability of that second card being an ace given that the first card is an ace? 1 out of 4. So notice that our numerator and denominator changed this time. When we did independent events last class, we were able to just do these probabilities to a particular power because the numerator and denominator did not change. The probability did not change, but this one did. What is the probability the first card is an ace? Sorry, the second card is a king given that first card was an ace? 3 out of 4, because there were still 3 kings left out of the 4 cards remaining on the table. What about the probability that the second card is an ace given that the first card is a king? 2 out of 4, because there were still 2 aces left out of the 4 cards. What about the second card being a king given the first card is a king? 2 out of 4, because there were still 2 kings left out of the 4 cards remaining. So if I actually wanted to find the probability of each branch of this tree diagram, now that's when I bring that multiplication rule back. Last class, the multiplication rule just told us to take the probabilities and multiply them together. So we use the power. But this time, when we go to multiply, notice that, again, these aren't the same fractions from event to event because we have some conditional probability going on. However, the multiplication rule still tells me that I can then multiply these adjusted or conditional probabilities together. So the probability that the first card is an ace and the second card is an ace, I would find by doing 2 over 5 times 1 over 4. You naturally did this when we did the Kahoot this morning. When we said the cards with replacement. Your brain naturally did this. It was doing conditional probability. I want this as a decimal, please. Can you give me 2/5 times 1/4 as a decimal? 1/10. 1/10. So it's 0.10 is how we'll write that. It was 1/10, obviously. But 2 times 1 is 2. 5 times 4 is 20. 2/20 is 1/10, so 0.10. If I was finding the probability that the second card is a king given the first card is an ace, or that I pulled an ace and then a king, I would do 2 over 5 times 3 over 4. 2 times 3 is 6. 5 times 4 is 20. 6 out of 20 is 0.3 or 3/10. The probability that the first card is a king and the second card is an ace, I would find by doing 3/5 for the first pull and 2/4 for the second. That's 6/20. Again, just giving me 0.3 or 0.30, 30%. And then the first card is king, second card is king, 3/5 times 2/4. That's the same number, so it's 0.30 again. So now I have this entire branching tree diagram that tells me all of the possibilities for this experiment. If I added these numbers up, this would be 10, 40, 70, 100. We have a 100% chance of these options happening, because there's no other option in this game. You either pull a king or you pull an ace. My question for you is, which of these branches of this tree was a win? The top and the bottom. The first one was a win, and the bottom one was a win. So if I'm trying to answer the problem for question number 4 that says, what is the theoretical probability of winning this game? I had to set up a branching tree diagram to see all of the options for winning. And since there are 2 options for winning, I'm going to add them together because I could win with an ace and an ace, or I could win with a king and a king, which means that my probability of winning this game is 40%. Now my question for you is 40%, but what did we get from our empirical? We were on the right way. I don't know about you, but I started off lower. I started at 30%. Some of you got way better than me. But as we keep adding trials and trials and trials, we're going to get closer to that theoretical probability. That's the law of large numbers. So the question that's going to come up today, and the kind of vocabulary you're going to see, is a lot like question number 5. It says, what is the probability that the first card was a king given that the person won? I want you to take a highlighter right now, and I want you to highlight that sentence, given that the person won. When you see the word given, this is now a conditional probability question where we have to use a different formula than we did before to find this probability. In theory, your brain would understand the concept of conditional probability already. In fact, it did. You guys were able to answer all of these questions, which was adjusting the total number due to what happened the first time. That's the main concept with conditional probability. If we're finding the probability that the first card was a king, given that the person won, and I'm going to use the formulas because I think it's helpful, we would say the probability that a person won, that a first card was a king. That looks like not what I'm trying to say. The first card is a king. Let's try writing that differently. First card is king. Now it doesn't look like a word. Given that the person won. When I said the word given, what did I just draw on my paper? Probability that the first card was king given that the person won. Okay, thank you for saying that. It's not technically a fraction bar. It is a straight up and down line. So on purpose, it's a straight up and down line. That is the word given in mathematics. Not if it's tilted, that's when you get your divides, but straight up and down is the word given. Okay, pretend like it's straight up and down. Don't judge me for my handwriting, okay? Okay, when we're finding this, what we want is the probability that both will happen over the probability of the total of the given. The probability of both of those things occurring over the probability of the given. We've found both of these things already. The probability that the first card is a king and I won, so if I'm using correct letters for this problem, that's really saying the probability I got a king and I won. I'm back to writing that first. Over the probability that I won. We just calculated the classical probability that we would win this game. That was the answer to number 4. So the probability that we would win this game is 0.40. Now we need to know the probability that we would get a king first and win. 30. Because the only way I can get a king first and win is by following this branch of the tree. Get a king first and win. So I'm looking for that overlap, if you will, the and between them. If we do 0.30 over 0.40, that's 0.75, or a 75% chance of pulling a king first if we won. And this makes sense because there were more kings than there were aces. So you have a higher chance of winning with kings than you have with winning with aces. That's why this number is so large. Comments, questions, concerns? Second page of these notes is really going to dive into these conditional probabilities. The idea that one thing happening given another is what we call this conditional probability. We started to introduce this last class with the evil eyebrow and the taco tongue, but it was super informal. And today we're going to formalize all of these different definitions. The idea of conditional probability helps us determine if two events are independent and helps us calculate probabilities that events that are dependent, that are not independent. Because last class we only used independent events. And in theory, the given probability is what actually helps us determine if something is independent at all. So today is a more generalized probability day than last class was. So if we look at this example below that has gender and marital status of residents in the U.S. age 15 and up in 2021. So we have gender as the columns, and we have marital status as the rows. This is called a two-way table or a contingency table. You guys also saw this on the Kahoot we played earlier, so naturally your brain understands how to read these. First question is just a review. What is the probability that a randomly selected individual never married? Well, if we're finding the probability that they never married, we just need the number of people that never married over the total. So what was the number of people that never married based on this survey? 92.7 out of how many people totally surveyed? 271.7. This whole time we're going to be rounding these to 3 decimals. Go ahead and pop that into a calculator for me. We're going to round that to 3 decimals. We should get for this 0.341. Yes? Okay. That's the probability that a selected individual never married. Part B goes on to ask, what is the probability that a randomly selected individual never married? Same question. Given that they are male. The moment I read the word given, I'm going to pause, and if it was on paper, I'd highlight it. Because if I know something about the population, I know that we're only talking about the males, I have changed the total. What is the total number of males in the survey? 133.6. That is now the total I'm working out of because it's a given that we're only looking at that column. It's a given. So if I were writing this one down with the correct formula, I would say the probability that a randomly selected individual never married, given they are male, would be found by finding the overlap between never and male over the probability, the number, sorry, not probability, and probability too, over the number in the survey that are male. My total has changed. In the first question, I was using the total. In the second question, I'm using the number that are male. So if we find that overlap, by the way, what is the overlap between never married and male? 49.5. So 49.5 divided by, this is going to be that new total, 133.6. Throw that into a calculator, and again, you would get 0.371. Question C says, what is the probability that a randomly selected individual never married? Same question. This time it's given that they are female. So again, we're changing the population that we're looking at. We're changing the given. We're changing the total. The total number of females in this survey is 138.1. So I'm going to be using that as my total as opposed to the total or the male total. This question would be written as, what is the probability that an individual never married given that they are female? Which means we're looking for the number in the overlap where never and female overlap. And we're going to divide it by the number of females from the survey. The number on top in the numerator, remember, is the overlap between them, is the and. How many in my survey were never married and female? 43.2, that's what goes in the top. Because I'm looking at the overlap divided by the total. Throw that into a calculator, 0.313 is what you would get. The next question is going to ask me, are these events independent? Independent is saying that knowing the probability of one does not affect the probability of the other. Is that true in this scenario? Does knowing the chances of them being male or female change the probability compared to the entire population? Are all of these numbers the same? Wait, are all of these numbers the same? No. Since the probabilities changed based on given or conditional probabilities, we now can confidently say that no, these events are not independent. Knowing they were male or female, oh, I missed a word, changed the probability. If these events were independent of each other, the probability, given that they're male or given that they're female, would be the same as the entire population. But since those probabilities were different, knowing one of the things affected the other means that they're not independent anymore. Do a couple more examples with the same table. I'm not really going to be able to show you both at the same time, so you'll have to look at your own. But E and F kind of go together. The first question for part E says, what is the probability? I don't know what just happened in my brain, but everything just short-circuited. What is the probability that a randomly selected individual is a widow, given that they are female? Again, okay, we see given. This is the same total we just used, because we're still saying out of the females, what is the probability that they are a widow? If I were to write this down as a formula, I would say I'm finding the probability that an individual is a widow given that they are female. So I'm looking for the number of the overlap between widow and female. And I'm going to divide it by the number that are female. Divide it by the given. So y'all look up at that table. What was the number of people that are widowed and female? 11.5. So 11.5 was the overlap. The same number is my total from question C. 11.5 over 138.1 is 0.083, or 8.3% of females are widows. On your own, I want you to read question F. On your own, read question F. Is that the same question as E? It's flipped around, right? This time, what is the given? The given this time is that they are a widow, which means our total is not out of the females. Our total is out of the widows. Look back up at your table. How many total widows are in this table? 15. That is my new total because that's what's been given. So as I go to write down this formula, sort of, the formulas would change. We want to make sure we're doing this order correctly. So the female given widow is how you would write this. The overlap is still the same because the overlap between widow and female and widow are literally the same location on this table. So you're right, that part didn't change. But what is going to change is the denominator of this fraction, because this time we're counting out of the total widows instead of out of the total females. So the overlap number is still 11.5, but we're going to use that green number of 15.0 as my new total. Now before you throw this in a calculator, because I'm your math teacher, I'm going to make you think about math. Is this fraction going to give me a bigger or a smaller decimal? A bigger, because 11 is way closer to 15. So we're having more of this fraction represented in our numerator. Now go throw it in a calculator. Ari, I would do this one. What do you get as the decimal? 767. So 76% of widows are female, while only 8% of females are widows. So what I wanted to bring to your attention here is that the way that the question is asked dramatically changes how you answer it. Make sure when you're doing conditional probability, you're using the correct total or the correct given. Does that make sense? So the last page kind of ends the same way we've been ending notes before, where we have a bit of vocabulary. I have, again, the formulas for conditional probability that we've been using. It's the probability of the overlap, or the number in the overlap, divided by the probability of the given event, or the number of the given, if it's a contingency table. But what this leads us to is the general multiplication rule. Last class, don't write this down, just listen. Last class, we found that the probability of E and F for independent events was the probability of E times the probability of F. How is this one different? This formula, this is from last class, and that was for independent events. It's because of the given. When we have dependent events, we can't just multiply them together because the first one affects the other one. So when we are trying to do multiplication, the multiplication rule for dependent events, this is the generalized formula that we would do the probability of E times the probability of F given E. In an independent scenario, the probability of F given E is unaffected by E. So these would end up being the same number. But in a dependent event, this one would change based on the outcome of E, which is why this is now called the general multiplication rule, because it fits both independent and dependent scenarios. So again, we learned that last class, but now we have a way more general multiplication rule that works for both independent and dependent events. You're multiplying the probabilities together. It's just that if it's independent, go for it. If it's dependent, pause and make sure you're using the correct conditional probabilities for the second thing. Are we ready to try some example problems? What I would like for you to do is I would like for you to do problems 1 and 2 on your own. Don't go to 3 yet. I want to talk through 3. But I want you to try 1 and 2. I'm going to give you about 3 minutes. For the first question that says the probability of drawing a red card from a standard deck is 0.5, when I read that, my brain was like, okay, probability of red is 0.5. I like to write them down as probabilities in the way that we write them. The probability of drawing a red ace is about 0.4. So this is the probability of red and ace, because a red ace is getting red and ace overlapped at the same time. What is the probability of drawing an ace given that the card you drew is red? So if I'm wanting to find the probability of getting an ace given that I know I picked up a red card, that means my total, it has to be out of the reds. That's my given. So that probability of it being red went in the denominator. But my formula for probability then just says to put the overlap on top. So I would do 0 or 0.04 over let me do that 0.5. And if you throw that into a calculator, you end up with 0.08. Bless you. Bless you. 8% chance of having an ace, giving that you drew a red card. For the second question, I'm going to probably do part C differently than you did. Don't erase anything until we get to the final answer because I want to show that there's more than one way to have done this. Number A says, what is the probability you get 2 red marbles? Well, there 3 are red and 7 are blue, and I'm not going to replace them. So that means the first event, which is drawing a red, is I have a 3 out of 10 chance of that happening. The second event, I have to think about the conditional probability. I've already pulled a red marble, which means there are only 2 out of the 9 that are left. Your brain naturally does this. This is conditional probability. You multiply those together, and Ari's favorite number appears, 0.067. When I did the second one with the blue marbles, same concept. The first time I reach my hand in this bag to pull out a marble, there's a 7 out of 10 chance of me getting a blue. And then because this event affects the other one, we have to change the denominator. And now it's a 6 over 9. You do this math, it's 0.467. Now for the last one, what I'm assuming you started to do, whether or not you finished it, is think, okay, well there's a way to get a red and a blue is to pull the red and then to pull the blue. Or I could pull the blue and then pull the red. So we'd have to find those probabilities individually and then add their probability together because there's 2 options. You can do that. Or you can use the concept of complementary probability. The probability of me pulling 1 each is the opposite of pulling some that match. Because my options are either they match or they're opposites. So I can find through conditional probability, this probability that I pull a red blue or blue red by doing 1 minus the combination of the probabilities we already found. So if I do this, I already found the matching probabilities. It's 0.067 and 0.467. And if I calculate 1 minus those combined probabilities, I end up with 0.466. Question number 3 says, the data in the table below represent the age and political party of a random sample of registered voters. The first question is, are the events Republican and age 30 to 44 independent? Now, this is not asking you mutually exclusive. I'm asking you for independence. That means knowing the probability of one thing occurring should not affect the probability of something else occurring. So we need to find those 2 probabilities and actually compare the numbers. So let's do the easy one first. What is the probability that we find a randomly selected individual and they're Republican? What's the total? 2,200. I wrote the wrong number. 2,200. Over the total, which is 4,000. We'll fast forward because you can put things in your calculator. That's 0.55. If this is independent, if Republican is independent from 30 to 44, that means we can find a conditional probability with these 2 together, and the probability should be the same. So what we're going to find now is the probability that we select a Republican given that we are looking at the age from 30 to 44. If the number we get from this conditional probability is the same as the regular probability, we can say they're independent. That means I need the overlap. What's the overlap between Republican and 30 to 44? 340 over the given total. What is the total number of 30 to 44-year-olds? If we throw that into our calculator, we end up getting 0.47. So the question is, are they independent? Are those numbers the same? No. So these are not independent. They would be independent if the conditional probability and straight up regular probability for these events were unaffected. Second question, are the events Republican and age 35 to 64 mutually exclusive? Ooh, throw it back to our Kahoot from this morning. What did mutually exclusive mean? No overlap. Does this one have any overlap? Wait, we really can't tell in this table if there's an overlap between these two events? Here's Republican. Here's 45 to 64. Is there an overlap? Yes. So we say that these are not mutually exclusive because the probability of Republican and age 45 to 64 is not equal to 0. If it was equal to 0, you say yes for mutually exclusive. Different word for mutually exclusive is disjoint. Last question. Are the events 17 to 29 and 45 to 64 mutually exclusive?
No. Wait. Yes.
This one is a yes. They don't overlap. The probability of picking somebody who is both 17 to 29 years old and 45 to 64 years old, impossible. That's equal to 0. We shouldn't have needed a table for that one because could somebody be in two different age groups at the same time? No, Ari, they can't be in two age groups at the same time. Don't make it weird. So again, mutually exclusive is looking for the overlap, and that is a different question than asking about independence. Independence is if knowing the probability of something else affects the probability of the next event. Different than mutual exclusivity.